the low budget reminder. Newton's second law is actually more about inertia than it is about force. And we had a conversation about that, but I want to bring up some phrases that were uttered in here as a place to begin. One of those phrases was that the effectiveness of a force. Remember that phrase? How effective is a force at changing an object's motion? When we compare this relationship, M determines the effectiveness of a force to cause a change in motion. It's that portion of the problem or that portion of the relationship that's about inertia. We define this as inertial mass, and I brought up often the distinction between gravitational mass and inertial mass. But it is this quantity that determines how effective a force will be. This side is what you do to the object. Or if you'd like, system. This is what happens to the object or system. This is observable. We can see it happen. We see the object change direction or slow down or speed up. This one may not be observable. It might be a force that we can't see. But oftentimes, it's a combination of factors that acts on the object. So friction, air resistance, tension, normal forces, gravity, all those things combine, and that becomes what we do to the object or system. Or sometimes we're trying to reduce those effects by placing the object in such a certain arrangement in which those effects might be minimized. The only thing that's really here about the object is its inertia. This is something that is about the object. And when we first started talking about this first semester, the whole thing was that bigger objects are harder to change. That's all we talked about, right? We just said if it had more mass, it would be more difficult to start into motion. It'd be more difficult to stop its motion and more difficult to change its motion. Which is why whenever we talked about what happens, oftentimes we would see things about the mass in the denominator. That's what we just saw, right? In our last example, the acceleration was 1/6 of g. The 6 came from the fact that it was 6 times the total mass, right? It was in the denominator. In fact, if we hadn't canceled everything out, we would have had mg divided by 6m equals a. This m referred to what we did to the object. We allowed gravity to act on it, right? That's the gravitational mass. Down here, this was the inertia of the system, and that m referred to the inertial mass of the system. Does that ring a bell? That's why mass ends up being in the denominator a lot for stuff like this, because inertia tries to prevent changes in motion. So we tend to see mass in the denominator. Yeah, I agree with you. There was no m in my answer. It's 1/6 a, but don't you realize the 6 is a result of the mass just being proportional to each other? I need you to know that. Because at some point or another, it should be becoming clear that when we deal with inertia, it is this ratio of something that we do divided by something we observe. That m is the inertial property here. Just taking the same thing and solved it for m, it's no big deal. Still just Newton's second law. If we're going to try and capture what happens to objects that are spinning, if you haven't yet kind of seen it, there seems to be some parallels between translational motion and rotational motion. Have you seen that a little bit? We don't have force necessarily for rotational motion. We have torque. It's how the force is applied. It makes a little bit of a difference. It's a little more complicated. But net torque would be what you do to a system. It's how the forces are applied to cause the object to try and spin one way or the other, or to slow down or speed up. We've talked about the fact that the result of an unbalanced torque an unbalanced torque, would likely be to change the motion of the object. So I would expect that there's a certain what happens and a certain what you do to the system. But you understand there's got to be something in here, right? Something that is about the object, about how effective are those torques at causing the object to change. Something in here about inertia. Now, I want to talk to you about rotational inertia for just a few minutes. I want to convince you of something. And it might take some convincing to do so, which is why you have your stopwatch. We're going to call this not rotational inertia, even though that's exactly what it is, but the term that we use is moment of inertia. I'm not trying to make this hard. We have to learn the vocabulary of our class, and moments are a thing in physics and in measurement. We are going to use an uppercase I. That's good, because at least it seems to correspond with something that we're measuring, inertia. And the moment of inertia is rotational or angular inertia. However, you should put in your notes something that you just determined from observing what we did in class, that this, whatever this is, depends on something. What does it depend on? I would say first, how the mass is distributed relative to what? Sure. Relative to the axis of rotation. Now, the historical use of the word moment here goes back a long way, and there's a lot of other reasons why the word moment is used here. But part of the reason it's used is because the moment of inertia is the inertia of the object at the moment it's being spun. Because a single object can have lots of different axes of rotation, its inertia isn't set until you set the axis of rotation. So consider just the meter stick example that we're using right now. There is a moment of inertia that is from me spinning it about its center this way. Right, that's a moment of inertia. But without changing anything about the mass or shape of the object, I could just as easily change the axis of rotation to be right there. And suddenly, without changing the mass of the object, I have changed the moment of inertia. So when we say moment of inertia, the reason the word moment is used there is to recognize that the moment of inertia depends on the axis of rotation. So for the same object, I could have an infinite number of possible moments of inertia, for there are lots of different ways I could spin the object. I could even tie a string onto the object and attach it in such a way that it spins relative to some place off of the object entirely. And that would also be a moment of inertia for my object, for it is spinning about some axis of rotation. Now, there are a couple things about this that I do want you to know. One of them is that if you fix an axis of rotation like we're doing, you can force an axis of rotation to be used. That's what we're talking about, choosing an axis of rotation. So when I'm holding this in my hand, I can determine exactly which axis of rotation I want it to use. Now, if you just throw something into the air, like say a flag or a gun, objects will naturally rotate about their center of mass. So when left to itself to spin, objects will naturally rotate about their center of mass. There still might be multiple axes for that, but they will naturally rotate about their center of mass. This is AP Physics C, right? When we talk about moment of inertia, a piece of mass here, like I said, will contribute less than a piece of mass here. If we could break our object up into pieces, we could find the moment of inertia. The moment of inertia of a group of objects is a sum. Each piece of the object contributing a certain amount to the moment of inertia. So if I break it up into, say, I don't know, some number of pieces, so starting from piece 1 to piece n, each piece not only contributes to the moment of inertia based on what its mass is, but how far away from the axis of rotation squared. So if I look at, say, this piece and make this piece 1, this would be R1. And this other piece, R2. If I'm taking the meter stick and breaking it up into individual pieces, each piece might have the same mass. But do you realize that the mass at R2 contributes way more than the mass at R1? Now, when we talked about center of mass, remember how each piece contributed in a linear fashion. So if I doubled how far away it was, it contributed twice as much to the center of mass. But in this instance, if you double how far away a piece is, it contributes 4 times to the inertia. So pieces far away contribute a lot more because it's squared. Now, unfortunately, there's a problem with using this formula. This works great if you can take your object and break it up into individual pieces. But you understand, for a smooth object, this part of the mass will contribute less than this part of the mass, right? If we really want to do this right, we have to break that mass up into a very small piece. You kind of understand where this is going, don't some of you? Do some of you understand what's probably happening here? That if we really want to find the moment of inertia for a continuous object, we will probably have to break it up into infinitely small pieces of mass and sum them over the entire object. You will have to be able to learn how to do both. And I'm going to make you, well, make is the wrong word. I will help demonstrate for you some of the basic shapes. We're going to do this second, and what we'll do first is we'll learn how to use moment of inertia first. So if you've taken a moment and looked at your homework, you know that I have provided you with a table of moments of inertia. Now, a table is something that if it were me, I would strongly encourage you to kind of get up here. I'm not saying memorize per se. I am saying that you will be far better able to utilize this information if you understand that first, you don't have to memorize very much, but if you memorize just a few things. For example, the moment of inertia of a rod. And when we say rod, we're just talking about something length L, mass M. About its middle, it's 1/12 ml squared. But about its end, it's 1/3 ml squared. It is 4 times harder to spin it about its end than it is to spin it about its middle. But also, be smart about this, you guys are. This axis, this little red line that you can barely see, do you guys see what I'm looking at now? This would also be 1/12 m, but not the L for the whole length. It would be how wide it is. So maybe W squared. But it's still about a center. You see, you would treat a bar about its center even if the bar was super long. If the bar is just this wide, then it's a bar about its center. Just like the door. We're going to treat the door like a bar about its end. Doesn't matter that it's long. Remember, the whole thing is about how far the mass is relative to the axis of rotation. If you're looking down the door, you just see a bar rotated about its end. So we'll treat this just like that, 1/3 ml squared, where L is this measurement. The M will accommodate the fact that the door is long, is tall. right? I mean, that's what makes this piece of mass right here contribute the same as this piece of mass right here. You follow? They're the same distance away from the axis of rotation. So when we look at things that spin, just knowing a bar tends to tell you about a lot of different possible shapes that might spin. Just about anything that's flat, if it's spinning in such a way that its cross-section looks like a bar, it's a bar. Then there's all the circles. Right? There's a lot of different circles, aren't there? Disc, ball, solid sphere, and maybe a ring. If all of them have a radius of r, and a mass of m, a disk is 1/2 mr squared. A hollow ball is 2/3 mr squared. A solid sphere is 2/5 mr squared. And a hoop or ring is mr squared, because all the mass is the same distance away from the center. This is assuming we're spinning it this way. It's a big assumption.